Hello, everyone. Thank you for joining us for the final showcase for the BioPREVAIL Built Environment Design Challenge. Today, you will hear from 7 teams who have made an enormous amount of progress since the challenge launched in the summer of 2025. The last time that you would have heard from us was in Geneva in December of 2025, and since then, all of the teams have moved into successful pilot phases of their technologies that are designed to improve the way that laboratories are built, function, and function sustainably. BioPREVAIL acknowledges the foundational support of Global Affairs Canada's Weapons Threat Reduction Program and the World Organization for Animal Health, and thank them for their support of the Built Environment Design Challenge.
My name's Keith Hamilton. I'm a veterinarian working for the World Organization for Animal Health. About a decade of work has gone into framing the first design sprint and working out what the best approach will be to find solutions to improve the sustainability of labs. So it's really exciting today to see the results of the first design sprint. And we've seen some really exciting ideas taken through to concrete solutions. And amongst those ideas, we're really seeing things that have high quality and relevance, and really looking forward to seeing those ideas translate into solutions on the ground in the coming weeks, months, and years.
This is Trevor Smith with Global Affairs Canada's Weapons Threat Reduction Program. We've been very proud supporters of BioPREVAIL and sustainable laboratory work for many, many years now. Because in the work that we have done over the past 20 plus years through the global partnership against the spread of weapons and materials of mass destruction to build sustainable biosecurity capacity around the world, we noticed a glaring problem: the lack of appropriate infrastructure for biocontainment diagnostic facilities in countries and regions that are resource challenged. They say that necessity is the mother of invention, so we decided it was time to invent. BioPREVAIL was created to provide a forum for innovation so that we could develop the type of new tools, new solutions that are going to be appropriate and support our partner countries, our partner biologists, those who work in facilities around the world. We believe that the Built Environment Challenge is a fabulous step in this process that will continue into the future. Thank you for your support.
Morning, everyone. My name is Paula Fernandez, and I'm the founder and CEO of GSS Health. And I'm presenting today a prototype that we've developed under BioPREVAIL that helps to support labs in rural places and far forward places for solar power. And one of the things about solar power in labs, having worked in the field in a lot of rural health systems over about 25 years, I noticed that solar power systems are not reaching the places they need to reach. And this is a really important problem, not just from running a hospital or a rural hospital, but also from a disease surveillance and outbreak perspective. And it's really a high stakes issue because every single power outage in the field widens the window for disease transmission. Delays in getting good diagnostics, delays in reporting, these all contribute to potential biosecurity issues in the field. And reliable power is absolutely a core biosecurity requirement. So BioPREVAIL allowed us to conduct a study using a commercial off-the-shelf system for solar power. And during this phase 1 study, we got a lot of feedback from end users, and we figured out some of the challenges with getting solar power systems into the field. And during that phase 1 study, which was conducted in 2 rural health centers in Kenya, we used a piece of equipment called the Gene Expert, which traditionally should go down to the lower and more rural levels of the healthcare system, but often it can't, and that's usually because of power supply issues. When we did take it to the rural health centers, one of which didn't have mains power at all, we were able to continuously operate it for at least 9 hours per day. We conducted 83 TB antimicrobial resistance tests and got 100% concordance with the referral lab results. We also got a lot of positive end user feedback. But there were some challenges with using the commercial off-the-shelf system in the field. And so what we did was we went back to the drawing board, and we developed a completely new system. And many of the things we did were to address the challenges with working in very difficult systems. In rural health centers, you often have a lot of dust. There are security issues. There are issues with supply chain, getting these modular units, commercial off-the-shelf units into the field is very difficult. The supply chain is quite complex. So what we did was we designed, I hope you can see it, a small box. And this small box, this is just the first prototype. This small box is very, very lightweight. And it is an enclosed system in the sense that it doesn't require fans. It has passive cooling. Fans are a problem in the field because they get dust and dirt in them. And we also redesigned the circuit boards in such a way that they're far more efficient. We can make them much smaller, and we can also greatly reduce the cost. In addition, these are very scalable units. So this prototype and the prototype that will follow it can be they're stackable. So they're actually really easy to ship in the field. And also it allows you to stack several units together so that you can operate just far more pieces of equipment in the lab. And together with the prototype, we developed a field power calculator. This is available online, and you can toggle between different pieces of equipment that you use, and it will give you the recommended configuration for your solar. Let's get back here. So we took our prototype and we went back to the field in Kenya and ran it again. This was the same rural healthcare center that we had been at before. And we did a lot of testing with how long it could run for, what was the most optimal way to run the tests in the field using the GeneXpert. And we found that 4 tests run together was the most optimal way. And interestingly, on a full battery without solar, we were able to do 93 TB tests, which actually is kind of surprising and really incredible. So 4.5 days worth of testing approximately. We had 100% reliability. We did a lot of analysis of cloud cover and recharging. And we actually found we got pretty good recharging even under some cloud cover. So what does this mean? It means that this prototype is able to reliably run diagnostics in the field. It allows equipment to run without depending on the use of fuel for generators, which is really important for operational independence, and enabled more tests to be done closer to the patient. And that is absolutely critical for disease outbreaks as well. And it's also a stackable solution, so you can scale up as needed for your lab. So the next steps for this project, we are working on a slightly new prototype based on the last round of data that we collected. We want to go through certification, electrical certification. Our next planned test site is in Ebi, which is in the Marshall Islands. If you look it up on a map, you'll see a tiny speck in the middle of the Pacific Ocean. They have a lot of issues there with power, especially after major storms. And then we're preparing to scale. So we're thinking about manufacturing and strategic partnerships. So I showed you a slide at the beginning that showed not just rural and resource limited labs, but we believe this system could be really useful for military and field forward operations. And so we looked at 2 potential applications of the technology, and looking at those, we're talking about somewhere in the region of 750 million of combined addressable market. But of course, for us as small business, we're not looking at that entire market, because I have to put a caution there that we're not currently built for large scale manufacturing. So we think that our niche might be a provider of custom high-performance solutions, especially the ruggedized versions, which you can't actually buy in the commercial off the system market. And just finally, to thank everyone at BioPREVAIL and the team at GSS Health, and also Christopher at 1983 Limited, who's our partner. Thank you.
Good day, everyone. I'd like to start by thanking you for the opportunity to present Contain and Sustain. My name is Emil Thanarayan, and together with Avi van Rensburg and Timelesa Lateka, we've been working on developing a low-cost effluent decontamination system, or EDS. Over the next few minutes, I'll walk you through the problem we're trying to solve, the solution we developed, what we learned along the way, and where we see the project going next. The idea of this project came from a challenge that a lot of labs across Africa face every day. Most commercial EDS systems are incredibly expensive to buy, and they're just as expensive to maintain. If something breaks, replacement parts often have to be imported, which can mean weeks or even months of downtime. Finding technicians who know how to work on these systems can also be difficult, especially in more remote areas. On top of that, many of these systems need stable power supplies and infrastructure that simply aren't available to every lab. When you put all of that together, it becomes clear that many facilities are left without a practical way of treating their liquid biological waste. So instead of asking, how can we build another EDS, we asked, how can we build one that's actually practical for the environments it's going to be used in? Our goal wasn't just to build an EDS. It was to build one that people could actually afford, maintain, and rely on. From the start, we focused on keeping the design as simple as possible without compromising performance. The result is a system that's around 90% cheaper than a typical automated EDS. Wherever possible, we use locally available components, so repairs can be done quickly without waiting for imported parts. The system is also flexible enough to be installed in different types of labs, whether it's a new facility or an existing one that needs to be upgraded. Because it's simple, it also uses very little power and doesn't need highly specialized maintenance. Most importantly, even with its simplicity, it still provides effective biological decontamination while meeting the required safety standards. Rather than designing the whole system upfront, we took an iterative approach and improved as we learned more. During the development phase, we designed the EDS but identified the need for agitation to ensure effective decontamination. At the start of the pilot phase, we researched and developed a simple, reliable agitation system before installing and testing the EDS at 3 pilot sites. Finally, we collected and analyzed the data from all 3 sites, allowing us to validate the system that was both effective and successful. When we progressed to the piloting phase, the system was installed and tested in real lab environments, namely at the University of Free State in South Africa, the Central Veterinary Laboratory in Zimbabwe, and the National Public Health Laboratory in Tanzania. These pilot sites allowed us to evaluate the system under real-world operating conditions. The feedback we received were opportunities for improvement. This iterative approach allowed us to refine installation methods, improve operator training, and optimize the system before final validation. The pilot phase taught us a lot. Like any new project, we ran into a few challenges early on. Firstly, effluent type matters. Some sites were using guanidine thiocyanate, which could be harmful when coming into contact with bleach. We then had design improvements. Minor issues such as leaks and installation challenges were addressed through design modifications and improved installation practices. We also had operator feedback. Feedback from pilot users were incorporated into operating procedures and training materials to improve ease of use. there was also design flexibility. The design approach remained adaptable, allowing the system to evolve based on operational experience and site-specific requirements. Lastly, we had standardized operating procedures. SOPs and training documentation were updated to ensure operators followed a consistent and repeatable decontamination process. To measure whether the project was successful, we focused on 4 main areas. Firstly, we successfully deployed the EDS at all 3 pilot sites, showing that it can be integrated into different lab environments. Secondly, validation testing confirmed that the system effectively decontaminated lab effluent before disposal. We also demonstrated strong system reliability, with minimal downtime throughout the pilot period. And finally, by implementing a standardized monitoring process across all the sites, we were able to consistently track performance, compliance, and operational data, giving us confidence in the results and helping guide future improvements. Overall, these outcomes showed that the system is practical, reliable, and capable of meeting the needs of real-world labs. Although we're really happy with what we've achieved so far, there's still plenty of room to build on this work. Looking ahead, our focus is on 5 key areas. We'll continue refining the design based on what we've learned during the piloting phase, develop a standard installation package, and carry out further testing to demonstrate the system's adaptability across different applications. We're also seeking a $50,000 grant to support the next stage of development and help prepare the system for wider implementation. Finally, we'll continue to build partnerships and increase awareness to encourage adoption across the lab sector. In closing, we'd like to thank BioPREVAIL, our pilot site partners, and everyone who contributed to the development and validation of this project. By focusing on affordability, simplicity, and sustainability, we hope the system can improve safe laboratory waste management across Africa and beyond. Thank you so much for your time.
Greetings, everyone. I'm Sarah Fernandez from the University of Cape Town, and together with Waste Not One Not International, we have done this work that's been funded by BioPREVAIL. So in order to test for the presence of HIV in a sample, you need to be able to access the RNA. And what I'll be presenting on is a chemical within these diagnostic tests, which has been of concern in the waste that comes out of these tests. So guanidine thiocyanate, which I'll otherwise refer to as GTC, is responsible firstly for breaking up the virus particle in order to liberate the RNA, and secondly for ensuring deactivation of all the virus particles so that the samples are not infectious. So really important in this process for these 2 reasons, and because it's so effective at doing this, it's a very toxic chemical. It's corrosive, it's harmful to aquatic life, and as we just heard in the previous presentation, it reacts with bleach to produce hydrogen cyanide, which is a really potent and toxic gas. And so all in all, there's been a growing realization that we need to treat this waste as a specific chemical waste. Just to put things into a bit of perspective, and if we look at the numbers involved here, so with about 40 million people living with HIV currently, this correlates to about 30 million tests done annually. And this in turn means about 1 million liters of this liquid waste is produced. And now the concentration of the GTC in this waste is also really high. It's up to 250 grams per liter, which, if that doesn't mean anything to you, it is really high, and it has the potential of therefore contaminating a lot of water if it was mixed in. So you could add at least 3 zeros to that figure and come up with 1 billion liters of water. So across many countries and labs where this test is undertaken in no small numbers, there's no current solution. And this is the flow of waste that we see across many of these labs, where it comes from the viral load testing platform. And in some cases, it's stored up because there is knowledge about the harmfulness of this waste, or in other cases, it's simply going down the drain. And so we came into the picture because we have a long history of treating thiocyanate within the mining industry. Because thiocyanate is a major component of concern within GTC, we've adapted our microbial system to treat the GTC within this thiocyanate, within this HIV waste. And the system has worked really well with more than 99% degradation, getting down to pretty much 0 grams per liter of thiocyanate left in the waste. So we love the system because it's sustainable, it's low cost, it works at ambient room temperatures, and one of the major costs generally associated with bioprocesses is the nutrients that you provide to the bacteria. In this case, we use molasses, which is a waste product from the sugar industry. It can also be a simple setup. So this is a typical bioreactor with all the bells and whistles. But we've trimmed this down to all you really need is a vessel, some sort of aeration, and some sort of agitation. And so this is what we've done, and this is our current setup in the lab. We've got a beaker set up on a magnetic stirrer and with a fish tank aerator. And so I'm speaking to you currently from Maseru, Lesotho, where we're engaging with the lab staff here, and we're running this trial and this method. And honestly, the lab has taken really well to the prospect of this solution. And so this last slide is really simple, but it's our real ask and why we're here now. So in the background, you see pictured this system operating at the mining scale. And so the systems, yes, there's small differences between them, but they're very similar. And so this gives us confidence that the system can be scaled. We know it can work. We're currently trialing it at small scale. The lab we're working with, we particularly chose it because they've explored many options of trying to deal with this waste. They do take this waste very seriously. The picture I showed earlier of the jerry cans stored up in that cage, that's from the lab I'm working with at the moment. And so, yeah, honestly, in my time here, we've been deep in discussions already about all the practicalities of what we'd need to set this up large scale at a level that would meet their needs and that could be sustainable. So they're really ready to uptake this. Yeah, honestly, with the way things have gone in the world lately, we're sadly expecting a rise in the HIV/AIDS epidemic. This is one piece of the situation on the ground that is generally overlooked. So this is us. We've come to the end of our funding, but we're really in the middle of this, and we really have buy-in on the ground to adopt the solution. So if you're listening to this and interested in helping set up a sustainable solution for these labs, we'd love to hear from you. Many thanks to BioPREVAIL and to all of our partners. Thank you.
Good afternoon, ladies and gentlemen. My name is Tembele Tumoyo, and I will be presenting the High Containment Laboratory Sandbox concept. The HCL, as we have come to call it, Sandbox project, was inspired by a collective desire to address the complexity of laboratory facilities built to specifications often developed in higher income countries. These have proven to be either unattainable or even unsustainable. And we found that some of the issues that are associated with these laboratory designs is they are insufficiently contextualized to the locality where they will be situated. There is an underutilization of the local expertise, and more often than not, the laboratory infrastructure is costly to maintain and often challenging to operate sustainably. We have developed, through a collaborative approach, we've validated and adapted the existing design of the sandbox in what we have called a structured co-design process. And this has led to the conceptualization of a comprehensive methodology that compiles design strategies, the participatory processes, and the technical considerations applicable across diverse environments. The project has demonstrated practicality following this participatory design approach to laboratory design. And our case study that we have drawn from is the National Public Health Laboratory in Dar es Salaam in Tanzania. And we have that has involved the participation of a broad range of stakeholders. The process has also demonstrated the utility of the high containment laboratory sandbox design as a suitable starting point for the architectural and engineering works for the upgrade. As we have been doing the pilot over the last 3 or 4 months, the methodology has been effectively applied in a low resource setting, as we say, that we've been doing this work in Dar es Salaam in Tanzania. And the process has also been locally led, and that has helped with the local team being able to decide whether or not the laboratory was needed and whether that will guide the sustainability of the design. This methodology, which has been crafted in 4 phases, was done across 2 National Public Health Laboratory sites, detailing exactly what upgrades were required to the non-functional BSL-3 facility. Out of this exercise, we have received insights on the required facility upgrade design and how to deliver a sustainable solution that is grounded in the local realities. Under phase 4 of this participatory design methodology, we have determined the end user requirements to select and adapt elements of the high containment laboratory sandbox design to develop an upgrade design of the Mabibo BSL-3 laboratory. In addition, we would also like to pilot the implementation of this methodology in other low resource geographical locations. So the ask from our team is we would like to expert review of this Mabibo BSL-3 lab upgrade design and detailed specifications. We would also be requesting support for the validation of the developed upgrade design and detailed specification of this case study, which we feel like will be groundbreaking for other low resource settings, as well as, like I've indicated, to pilot the methodology in other low resource settings. Thank you very much.
Good day, everyone. My name is Zine Baybay from Bioassets Corporation, Philippines. Oops. Animal disease outbreaks such as those caused by avian influenza virus and African swine fever virus have wide devastating impacts. In the Philippines alone, 76 out of the 82 provinces have already been hit by ASF since 2019. This has resulted to a 50% wipeout, or equivalent to a $3.2 billion loss to the livestock industry. Since 2021, recurring outbreaks have also resulted to culling of millions of chickens due to bird flu. Outbreaks move faster than laboratory confirmation. Around 60 to 70% of the livestock industry in the Philippines are backyard farmers and are in hard-to-reach areas. Producers, veterinarians, and government agencies still rely on distant diagnostic laboratories for confirmatory testing. However, their access is limited. On average, one regional animal disease diagnostic laboratory, or RADDL, serves at least 2 cities with 19 municipalities and around 2,500 villages. Some of these locations can be as far as 140 kilometers away from the laboratory. This causes delays in laboratory turnaround times, lasting around 5 to 7 days. In addition to that, the need to transport samples do not only cause degradation, but may also threaten biosecurity and cause more losses. This is a gap that we aim to close. BioAssets is a dynamic, science-driven animal health company focused on advancing livestock health system through disease intelligence, its own R&D, precision diagnostics, and rapid response. We combine on- and off-site laboratory diagnostics, pathogen genomics, and epidemiological data systems to support industry through the producers, veterinarians, and policymakers. With that, our solution is a mobile biocontainment laboratory for on-site confirmatory diagnostics. It was built to rapidly respond to outbreaks, ensure continuity of operation, improve decision-making, capacity building, and research and surveillance while maintaining biosafety and biosecurity. The prototype NBL successfully demonstrated its functionality through multiple testing activities and deployments with partner sites and end users. These evaluations validated the prototype while providing valuable insights for further enhancement. Key areas identified for improvement include optimizing the workspace, reducing engine dependence to minimize noise and vibration, improving cooling capacity, and enhancing equipment protection to further strengthen the MBL's performance and reliability. Through BioPREVAIL, we transformed our prototype into an evidence-driven platform, implementing targeted engineering improvements and validating them under real-field conditions. The development phase focused on engineering improvements, and later, the piloting phase focused on the deployment of the MBL to gather data on whether our mitigations made impacts. Consultations with past MBL users, local fabricators, and lead mentor redirected our team from expensive redesigns toward practical fixes that could be implemented and validated within the project timeline. On the left are the list of what we have initially considered, and these ideas have been parked for implementation on our next model. On the right are the practical and measurable implementations we have actually done for this project. Aside from the cost and timeline, several other factors such as delayed communications, importation delays, as well as natural disasters have also impacted our decisions. For this project, we validated the performance of the improved MBL on 3 pilot sites, surveyed 9 users, and conducted 22 environmental data tests and 28 vibration tests. For the results on the environmental testing, data showed that there was an overall improvement of the cooling system maintained at 27 degrees Celsius during operation. Our improvements included flooring insulation, addressing mechanical air conditioning issues, and including a protocol-guided parking location to mitigate the solar heat gain inside the MBL. On the other hand, vibration data showed that our mitigations reduced vibration during idle operations, and the appropriate transit casing may further dampen transit-related vibrations. We've also run several testings under transit conditions, but more data and appropriate equipment are still needed to further prove or validate our data. Overall, our data sets, which were gathered on all deployment, gave us the needed insight on how our mitigation measures have improved incrementally the primary issues we were facing. Lastly, this slide summarizes user feedback after each deployment of the MBL, rated in a 5-point scale across 11 categories. Overall, ratings were positive, for ease of equipment setup and feeling of safety scored the highest. Moreover, we group the open-ended feedback into what worked, the challenges encountered, and suggestions as detailed on your right. Most of the challenges indicated are also tied to our previous slides. Ultimately, our team, along with our lead mentor, saw ourselves at the end of the road for the MBL prototype with respect to this project. One of the great successes of this project is that we now own a complete set of data and comparative interpretation, which will allow us to develop and pursue building the next MBL 2.0. More specifically, we will improve on the working space, use a six-wheeler platform, improve insulation and make the cooling system fully independent of the engine, use our data for equipment placing and casing, and lastly, ensure sufficient power supply and connectivity. BioAssets has proposed the MBL as part of a national surveillance program supporting the RADDLs and local government units. We have also approached and identified 6 state universities with agriculture and veterinary programs as strategic partners for capacity building and research and innovation. So now, as we transition our focus towards the design of the MBL 2.0, we are currently seeking out resources in terms of funding to construct and validate the unit, technical expertise in mobile lab design, HVAC, vehicle engineering and biosafety, as well as strategic partners and funders, including guidance and sustainability. We know that this is a big ask and we'd be very grateful for any support or connections. We are confident that our MBL, which is locally designed and resource appropriate, can serve as a model that is transferable not only in the Philippines, but also to low and middle income countries facing the same hurdle. And with that, thank you very much to BioPREVAIL and to everyone who made this project possible.
Yeah, so thank you so much, team. So my name is Ronald Odero, leading the Research World team partnership in Kenya. So the project that we were undertaking was with regards to the SL Bioloc bin. With regard to the SL Bioloc, I'm not able to see my screen. Yeah, was with regards to the SL Bioloc bin retrofitting. So we conducted this pilot in Kenya, and we conducted this pilot in a region called Kisumu. So we were just to bring background with regards to what we were, carrying out. So we know that currently in healthcare facilities in Africa continue to rely on conventional biomedical waste bins. And this is to say that the current bins are not able to do the measurements of weight real time. And in addition to that, they lack a biosecurity measure whereby the bins are not locked and the top design is that they're able to be opened. That then results to limited traceability with regards to waste and accountability, and also biosecurity exposure within the facilities and the community at large. So in addition to that, an element of regulation and compliance with where the waste comes from and the management, that's also a gap that actually has been existing with the use of the current bin system. And therefore, we brought in the BioLoc bin, whereby this bin is a smart bin that has some intelligence platforms that was able to help in actually ensuring that we weigh at source and enhance the biosecurity element, whereby we have a locking system, and then through that ensure that we have capacity to enforce compliance with regards to tracing where the waste comes from. And in addition to that, use the local available material or the bin that exists by only retrofitting. So before that, we conducted a market, we did conduct a market discovery survey. And in that survey, we got that generally we had 63% of the facilities that were currently not weighing at all. We had also that there was no real-time monitoring of the data with regards to waste management. 55% were also reported to have poor waste containment practices. And also of the healthcare workers that we surveyed, 63% of the workers perceived that this was a real occupational health threat. In finality, through that survey, we got that about 80 to 90% of the surveyed healthcare workers were in support of our innovation. And that then led into us moving to the next level and putting proof of the concept. So what solution did we give? We proposed a retrofitting whereby we were envisioned that currently there are several bins that are existing in the facilities. And we proposed an approach whereby we'll just retrofit. And in this retrofitting, core elements that we were looking at was to enhance the weighing mechanism through a digital system, ensure that we have a smart alert system where we are using the SMS platform. And then we had a control access where the bin had a lockable unit, which we were using the lock system. And then manual locking system. And then we had a waste tracking system whereby we developed a dashboard that at every episode that waste is removed from the bin, a communication is sent to the leadership or the department in charge of the waste that a bin at location X is already being emptied. And it sends a message with core information, either it's being empty or it's full or it is just being opened. So that we're able to get those three signals. So in the pilot, we completed the pilot implementation. We looked at the concept. We looked at the co-designing with the 41 healthcare workers who are also involved in the process of co-designing the type. We then did a retrofitting prototype, which we then fabricated. And then we had a pilot in 6 facilities. So those were the key activities that were also conducted post the design session. So we came to the evidence and progress. That's why we were validating the innovation. So what did we do? We designed 7 prototype units, but we had 6 facilities that were piloting. And then we trained about 88 healthcare workers, where we had 62 male and 26 female. And then among that, indicated that 90% of the healthcare workers were positive on the perception and use of this system. And as you can see in the picture here, so we have a pilot facility in Kisumu. So this is how the installation of the bin was. So we were being given a location. We are able to connect the bin to the solar unit, solar for charging of the battery, and you can see the lighting on the bin. So then that is able to be mapped that the bin is functional. And then another unique thing that through the GSM system, these bins were mapped by the facility names and location. So this bin cannot also be transferred to another facility. It can only work when it is in that facility where it was mapped. And as you can see the photo here, this second photo, these are the stakeholders, these are the county officials where we did a stakeholder meeting. And these were the leadership from the Ministry of Health and the IPC officer who were in charge of the piloting. So when I went to the county, we were allocated an IPC officer, the one who is holding, and then the leadership of the laboratory, the lady in black. So this was the introduction approach that we conducted. Then we come to the facilities that were selected. We had a facility that was Kisumu County Referral Hospital, Lumumba Star Hospital, which was a private. Lumumba and Kisumu were districts or were public hospitals. Ahero, a public hospital. And then we had St. Elizabeth, which is a faith-based facility. And then we had the Railways Health Center. So this was just categorizing the facility based on the level of the services they provide. And as you can see on the side here on the far right also, we have a digital system that is the dashboard, which monitors the waste as they are being dropped across the various facilities. So anytime a change in weight is realized in a facility, we had in our dashboard that the graphs are being drawn across every facility. So in addition to that, we provided the facilities with SOPs. We were helping them to monitor wherever we were because we were accessing the dashboard. And then we were also able to have the categorization of the facility across the various levels of service. And then we also had the sensors power and the containment issues that were also emerging during the piloting. And we were also to monitor through the online system, and we are able to address them as we go along. So On the feedback with regards to use, this is post the pilot. The pilot feedback confirmed that high acceptability, where we had about 100% of the reporting operational improvement, and 90% of the users also expressed positive experience. And this 90% was associated with, 10% was associated with the issues that we could continuously have an issue where the battery could be lower, the sun could have been of less intensity to help us recharge, and also the issue to do with either sometimes some network-related issue that the relay of the data could not be real-time as they would actually wish. Then the retrofit approach was also considered very practical and affordable, as the bins are available in the market. So our work was just to target the module units that we were coming up with. So what we are talking about is actually the battery, and then the sensor unit, and also the database, which actually was integrated to the Ministry of Health ICT system. So then integrating this into the local facility data management was actually easy. We then had access to standard bodies and certification pathway that also facilitated us to be able to pilot this. And this was actually, the county was ready with this initiative. And also the Ministry of Health through the Global Fund officials were really positive and actually supported our implementation. So with regards to demand, so we did a market canvas kind of approach where we are looking at where is the market in the future. So we are just lucky that through this implementation, we were visited by one of the MOH, Ministry of Health Global Fund representative, and he was able to actually put a request for us that if we could actually be able to cost this item. And in addition to that, we were to also have one final well-refined unit that can be demonstrated to the Ministry of Health. Then with regards to scalability, through the same support for the county and the Ministry of Health official, we are looking forward to about 14,000 registered public health facilities. And in terms of projections, we were estimating about one facility having about a minimum of 5, and that then could project potentially over 70,000 units that could actually be anticipated. Some 2 new markets that actually emerged also in our evaluation was that there's an increase in the self-testing kits that people are using in households. And this is an area that in most estates we lack the medical containment units. I mean, the waste bins that are in the estates are majorly to handle household disposal. So we are looking at that as a potential area to be also targeted. And also the use of biolog could actually be also employed in disaster and emergency prone areas, more so potentially where there was, and actually accessing the disposal facilities might be a little bit challenged. With regards to sustainable impact, we are looking at a retrofitting platform that potentially could help us strengthen these units, strengthen this initiative, and actually be able to scale locally within the country, and by also tapping into the local capacity that is within the country. With regards to the next steps, we are looking forward to having a refinement of the engineering and having potentially feasible, stable units that are able to be, hard enough to be resistant with regards to facility utility, and actually be able to have the engineering for an industrial level that is actually helping the strength of the bin. Because the one we were doing for the piloting, several units were actually not finally attached, as we were actually joining them using the light materials. Then with regards to strengthening of the platform, we are looking forward to optimize the digital monitoring dashboard and the data analytics, and the feedback from the Ministry of Health. They were looking forward to us having a database that is able to show the 360 journey of the entire waste from one facility to another, because our disposal units are actually scattered across. Then we are looking at scaling. We're looking forward to expand deployment to more than 100 facilities and put proof of concept. So this is an area that actually we are looking forward for support. And also we are currently working with regards to finalizing our provisional IP registration with the KIPI, which is the body in charge of the registration in Kenya. And we did a provisional 1-year IP registration. Then with regards also to what we need to reach more facilities, we are looking at investment capital, and we are looking at towards funders who can help us to scale this and to support the refinement, that is the engineering part, then also be able to be supported to get the international IP registration, and also work with regards to deployment, working with the partners and also scaling up to more than the 6 facilities that we were targeting, and also trying to reach out to other counties. As a country, we have about 47 counties, and we are faced with the same challenge of waste. Therefore, looking forward to translate this potentially to a national level. I would also give acknowledgement to the Research World partnership teams. The Fab Lab team, this is the engineering team that actually assisted us development, and also they also helped us in the piloting and facility installation. As you can see in the pictures, we are in one of the facilities with the team, and we are so grateful to these young engineers who also help us to conduct this exercise. As we look, finally, I would just want to say thank you. But before we leave, you could just see the difference of the 2 approaches. The 3 bins are the current bin as they are, and the last bin with the solar unit and the lighter, that is the bin that we were retrofitting. Thank you so much, and that's all.
I'm Sofia Perez from Institut Pasteur du Cambodge, IPC for short. I'm the project lead for Collab, which is a waste-to-resource platform that uses circularity to design a new operating model for scientific laboratories globally, especially those in resource-limited settings. Every laboratory has a version of this story. The box is held together with tape or a spare part that is no longer available. And then there are the people behind the scenes devising makeshift solutions because the work just cannot wait. These moments don't show up in scientific publications, yet they quietly shape science and global health every day. One of those moments came to define the beginning of Collab at IPC when one of our technicians, Siredet, asked, can we make a better storage box? And so we began the BioPREVAIL Design Challenge by seeing if we can create a better solution. This was our starting point. As you can see, we needed more space, but buying another fridge every time we ran out just wasn't sustainable. We wanted better tools to house precious scientific reagents and samples, but the alternatives were simply too expensive. And global pressures are only pushing those prices higher. Meanwhile, the scientific and global health sector uses a lot of plastic, adding to a growing problem that's accumulating in our land, our seas, and our air. With Collab, we looked at how we could address all of these problems at once. Now, what you're looking at is a cold storage box made 100% from IPC's laboratory plastic waste. To us, this is more than a box. It's proof that IPC and similar labs can design and manufacture tools that fit their own needs while using resources efficiently and responsibly. These boxes are designed and made locally. They are durable. They save space, they stack securely, and are customizable. 9 months later, we have our answer, and this is what has changed. You can see on the left the fridge with the old storage boxes and the same fridge with the Collab storage tools. Of course, designing a product is only part of the job. It also has to perform and meet our needs. So we've completed our first round of tests, and I'm proud to say that we've gotten some great results, with 85% of the products passing the first series. And one of my favorite results beyond the test data is this. On the left, you saw Larama, who is one of our technical officers, beaming with pride while running the first series of cold tests on the boxes. And on the right is Siredet, the lab tech who asked us the initial question that started it all. He is testing the cold storage box he helped make possible within the virology unit, which is 1 out of 12 units at IPC. But this project is really much bigger than making boxes, or even bigger than recycling. It's also very much about unlocking the potential in people who make systems like Collab possible. In pursuit of creating a better biobanking tool, we succeeded in giving laboratory waste a second life. Along the way, we confirmed what we had suspected all along, which is that laboratories like IPC already possess the resources, the creativity, the knowledge, and determination to shape their own solutions. With the right partners like BioPREVAIL, and the support of all funders who made this design challenge possible. Those solutions can be developed from within using simple, accessible technologies that can be retained and sustained in the long term. These boxes are only the beginning of the story. With Colab, we can design a range of lab tools and spare parts that allow for repair of valuable equipment. This can change and be adjusted based on each lab's needs and capabilities. We can even expand our portfolio to non-lab items that are part of the scientific world, like institutional supplies, merchandise for events and trainings. Ultimately, though, Colab leads to a much bigger question. Can laboratories build solutions this way instead of waiting for them to arrive? At its core, Colab is about strengthening the people and systems that protect global health by leaning into creativity and sustainability rather than dependency. For years now, for the longest time, actually, laboratories have followed a linear model. Business as usual looks like the image on top. When we need something, we order it, and we sometimes have to wait a really long time. And then when it gets there, we use it and we throw it away. It's a model that takes agency out of our hands. It starts and ends outside our hands. Colab breaks that cycle. It's a new operating model where end users articulate challenges that are unique to them and co-design solutions. Colab turns these ideas into prototypes and then into local manufacturing in an iterative way. And every step and all the learnings and lessons carry forward into versions 2, version 3, version X of the same tool that they have designed. Imagine those lessons traveling as easily as scientific publications so that every improvement becomes a starting point for the next Colab to build on. Of course, none of this happened in a straight line. Every prototype taught us something. Every setback forced us to pivot, and every pivot made the model stronger and reduced uncertainty. And if you could look behind the scenes over the last 9 months, this is a glimpse of what it looks like. Over 9 months, we built workflows. We established a better waste management SOP. We improved our decontamination processes. We created new manufacturing pathways. We even built a dedicated Colab space. We designed V1 and V2 prototypes. We created handbooks and dashboards and produced our first laboratory products using IPC plastic waste. In the end, this challenge gave us so much more than a product. It gave us a platform. It gave us an operating model. Today, Colab has a physical home at IPC, a compact system that can be built in research institutions anywhere. It has a committed team, it has a process, it has proof, and perhaps most importantly, it has momentum. From the pilot phase, our numbers show that we've collected 1 ton of laboratory plastic. And in less than a year, we have transformed 75% of it into usable raw materials. What makes that even more striking is that we're only looking at 2 types of plastic so far. And we love these numbers because they give us confidence in what's possible. They tell us that this works. But the greatest impact truly begins the moment this knowledge reaches the next laboratory and the next and the next. Once 10, 30, 100 labs can look at their own numbers and say the same thing. Basically, we've diverted X tons of plastic from our landfill and transformed them into usable materials. That's when we know we've made the greatest impact. So I invite you to imagine 2 technicians, Visal and Sonita, at IPC. They're wearing white. They have a challenge, and they decide to work with the Colab team to design a solution. The solution and lessons help another Colab in Laos, maybe another Colab in the Philippines, another one in Cameroon or in Madagascar. Knowledge moving across Colab network, giving each a better starting point than the last. A network of laboratories becoming stronger together. Science has always advanced because knowledge is shared and because new discoveries build on previous discoveries. Colab extends that same principle to the way laboratories operate. That is the collective intelligence that Colab is building. But how do we get there? The next 12 months are about moving Colab from a successful pilot to a fully operational model and preparing it for replication. These 6 months are crucial as we move to validate the business model within IPC while making the operational framework stronger. We will continue documenting what works and what doesn't, adding to our design capabilities to build a model that others can adopt. We're looking right now for strategic partners who are willing to invest in this stage of Collab's development, to strengthen the science, to develop our technical capabilities, engage external quality assurance teams and life cycle assessment assessors to uncover the full potential of Collab within and beyond IPC. These activities will all need funding. Our ambition, of course, extends way beyond a single laboratory. Over the following 2 to 5 years, we want to deploy Collab in at least 50% of the Pasteur Network laboratories. What begins as local resilience becomes a global network of labs that are better equipped to respond to global challenges that we face today. The question is no longer whether laboratories should become self-reliant. We know the answer is yes. The question is who will help build the model that makes it possible. Collab is the blueprint. The path is already in motion. Help us build it. Thank you to BioPREVAIL, the Collab team, and to IPC who helped turn an idea into reality. Thank you.